first try to bring in the most timely, wonderful topic and give you the best research, top researcher in the world. Try to give you the one of the most important subject. And this year we try to have program last about 4 weeks. So about 4 great speakers going to talk about this program. And this year our topic is deep learning method and theory. We're very proud. My big longtime hero, Larry Carin, is going to give a wonderful seminar today. Just make it brief. I know Larry, there's no need for introduction. Everybody know him, but I'll try to say a few words. He got his PhD from University of Maryland, one of the Big Ten schools. And he is currently the Marion Distinguished Professor, a very well-known researcher in the whole world. He's also a wonderful, great administrator. That's amazing to me. I thought that's 2 different abilities. He's now the vice president at Duke. Just give you some idea what vice president looks like. If a department head like me is the Earth, then the dean is a Jupiter. In that case, vice president like a sun. So that's capacity he had. Larry, I'm going to give more time for Larry. Thanks again for Larry to take it's very super busy time. He's going to give a decent research topic in the afternoon and give a tutorial, give you basic understanding for deep learning, so you can learn from first hand the top researcher about what deep learning is all about. So by that, let me cut off here. Larry, it's all yours. Thank you so much.
Okay, thank you so much, Dennis. And it's a pleasure to be with everybody this morning. Purdue is one of the great universities in the country, and it's an honor to speak to you today. So I'm gonna give 2 talks today. This morning is going to be a tutorial. It's going to be I'm going to try to make it as simple as possible, and then this afternoon will be more about state-of-the-art research. So this morning, my goal is just to give you a sense of what deep learning is. And then this afternoon, we'll dive in a little bit deeper. I know that this is a statistical and mathematical audience, but I find that sometimes all of the math can some of the key ideas, the underlying intuition about why this technology works. And in fact, one of the issues with deep learning is that a lot of people view it as a black box, and what that means is that not a very clear understanding of what is going on and why it works. And so what I want to do is to focus not on equations, but to focus on intuition, to try to understand why it is that deep learning can work. And so let's dive in. So I'm going to try to be very simple and intuitive. So let's imagine that we have a set of images that we wish to analyze. And so this problem comes up all the time, analysis of images. For example, in pathology, we look at images under a microscope and try to do diagnosis. Then other areas, facial recognition, etc. So image analysis is an absolutely area of data analysis. And in fact, it is the area for which deep learning first demonstrated its extraordinary capabilities, although today we've moved well beyond images. But in any case, we're going to focus on images, and one of the reasons of that, in addition to the importance of images as an application, human beings tend to be visual. And so by looking at visual data, hopefully it'll give us some intuition about what is going on in deep learning. But the concepts that we're going to talk about extend beyond images. Okay, so let's imagine that we have a set of images that we're going to try to learn with. So what I'm showing you here are 3, and then a 4th cartoon images, obviously cartoon. So it's meant to be illustrative. But imagine that you have images that look like you see here. And the underlying characteristics of the images that I'm going to show you here are indeed characteristic of real images, although the details are different. So imagine you have a bunch of images. What we would like to do, so the problem is this: imagine that you're given a set of images, of digital images of what cells look like under a microscope. And what you would like to do is to automate diagnosis of pathology using deep learning. And other areas where you would do this, for example, an analysis of images of the eye. And this has been done, for example, for diabetic retinopathy. And in all of these fields, by the way, deep learning has proven to exceed the performance of a highly trained clinician. So the performance is extraordinary. So in any case, the game is we're given a lot of images and we're given the human diagnosis of those images. And then what we'd like to do is to train a machine to do that process. So here, let's assume that these are the images, just for argument's sake. So what are the characteristics of these images and what are the characteristics of images in general? So typically there are high level, what I'll call motifs that exist within the image. And these are the motifs of my cartoon images. So again, go back to the images, look at these. These motifs are located within the images, different motifs in different images, and their location varies. Now, if we look at these motifs and look at the structure within these motifs, we notice that the different motifs share underlying structure. So notice that although the motifs are different, many of them share this canonical shape. And then here is another canonical shape that's in the motifs, and another canonical shape. So the thing I want you to notice is there's kind of a hierarchy, and that will become clear in a moment. And here is that hierarchy. So the point I want you to try to capture, or at least the intuition for deep learning, is that the data are characterized by high-level motifs, what I call layer 3 motifs. Those high-level motifs are themselves composed of sub-motifs. And then those sub-motifs are composed of fundamental building blocks, which you see at the bottom. This intuition is the fundamental concept, fundamental intuition of deep learning, is that there is a hierarchy in the way in which we can represent data. At the bottom, we have very simple atomic structure. At the next layer, we have combinations of that atomic structure. And then at the next layer, we have combinations of those combinations. And then this can go for many, many layers. And in this way, we can go from very simple building blocks to very complex images. Now, if you think about this, there's a lot of intuition here, or a lot of similarities that you can imagine in nature even, right? We have cellular organisms, multicellular organisms, and then very complex organisms. But the underlying fundamental building blocks are shared. This is the key intuition. So now, how are we going to take this intuition and put it into a mathematical or statistical construct that we can actually do analysis on? And so let's go back to our images, just to remind you. So we have these images. These images are characterized in terms of motifs. And then everywhere where you don't see anything, let's just say it's noise, or at least it's something else. And this is very typical. So how are we gonna do this analysis? Okay, so let's now look at one of these images. And let's go back to our fundamental building blocks. So these are the fundamental building blocks at the bottom. What we're going to do is we're going to take one of those building blocks here, this triangle. That's a filter. It's a filter. We're going to take that filter and we're going to slide it. We're going to shift it in a two-dimensional shifting throughout the image. And we're going to quantify the degree to which that filter aligns with the structure in the image. This is a two-dimensional convolution. So we take this filter, we convolve it in 2 dimensions with this image. This is the output of that convolution, obviously cartoon, so don't take it too literally. Red is strong, blue is weak. Notice that that triangle here and that triangle there match that filter. And so when that filter slides across this 2-dimensional image, when it's located over here, there's a strong correlation. When it's located here, there's a strong correlation. We get 2 strong dots. This is the product, this is the result of that convolution. Now, what we're going to do is we're going to do this for each of our canonical filters. So we're going to do it for each one of these filters at the bottom here. So we're and of course we're going to do it separately. We do it separately for each of these. So we take this filter, we convolve it in 2 dimensions across that image, and we get an output. We call that output the feature map. It's called a feature map. We then take this filter, 2D convolution across that image. We get a feature map. We do that for all of these. Those feature maps are quantifying the degree to which each of those filters matches the structure in the image. And so as a consequence of this, for each of those canonical atomic filters, we get an associated feature map. Feature map. So map is just a 2-dimensional mapping of the match of the filter to the image. And it's a feature. We're characterizing features of the image, so it's called feature map. For every canonical filter, we get a different feature map. We stack them together. We stack them and we align them spatially. And so that's what this is meant to indicate. So at the output of this process, a set of feature maps which quantify the degree to which these atomic elements match local regions in the image. But remember, we go back to our structure. We have now only characterized the bottom layer, the most primitive structure. So now the question is, how do we find the second layer of this hierarchy?
Dr. Carin, can I interrupt you?
Sure.
We have a question. Someone's asking, are the filters pre-specified? So
at this moment, yes, but of course in practice, no, because we don't know them. So there's 2 answers to that. In the toy example, the answer is yes. But in reality, of course, we don't know the filters and we're going to learn them. And I'm going to talk about that in a moment, but it's a great question and we will get to that. So at this point, assume we know the filters, but of course we don't know the filters. So this is just giving us the intuition. And then subsequently, we're going to go ahead and we're going to learn it. Okay, so now we want to go after the second layer of hierarchy in our features. And so now let's look at this layer 2 sub motif and using the language that I used before. So this is the layer 2. And so now look at this. This is a square, a triangle, and say an ellipse, right? And now the square feature map is the bottom one. The circle or ellipse feature map is the second one. And the triangle one is the second to the top feature map in our stack. Now, if this shape is constituted in our image, which means, of course, a triangle, circle, and a square in near proximity, then what we would expect is that this feature map would have a strong value, this feature map would have a strong value, and this feature map would have a strong value in near physical proximity to each other. Because this bottom one is our square, second one is our circle, second to the top is our triangle. If a square, a triangle, and an ellipse or circle are in near proximity of each other, then these feature maps should be strong. So therefore, if we wish to look for that submotif, we should build layer two filters, where to identify this type of structure, we would expect that, and notice that the filter is now a stack. So at the layer one, it's just a single image, little image. Here, it's a stack of images. That stack of images is aligned with this stack. And now what we're going to do is we're going to constitute a filter that has strength here, strength here, strength here, and then all the white is going to basically be 0. And then what we're going to do is we're going to take this filter and we're going to convolve that filter across the image. Now, think about this some more. Here's another one of those layer 2 motifs. So rectangle, different triangle, circle. Okay, so this is our circle, this is our different triangle, and here's our rectangle. So what we would expect is if that structure is within the image, then these filters, those layers of our stack should be high. And we could do that for all of the layer 2 motifs. And so now what I've done here is I've color coded these, and then I've highlighted the colors at which the stack will be high for each of those layer 2 submotifs. And then we play exactly the same game we played on layer 1. We take these filters. Now we're going to convolve with this stack. So this is meant to be convolution. So we take this stack, we do a 2D convolution with this big stack. Everywhere where there is alignment, in these shapes, we would expect the corresponding feature map to be strong. Okay, and so now we get a layer 2 feature map. The layer 2 feature map is now looking for layer 2 substructure. And then we play exactly the same game. This is our top layer motif. This is the much more sophisticated motif. Well, if this is present, then this will be present, this will be present, and this will be present simultaneously in near physical proximity of each other. Which means that since this is the bottom filter map, then this should be strong, the top one should be strong, and this one should be strong. Now, if we take that filter and convolve it across this feature map, we will be looking for these layer 3 motifs. And so we do exactly the same game. So the thing I want you to notice, couple of things. First of all, we're playing the same game at all layers, 2D convolution at every layer. So it's the same structure at every layer. The only thing that is changing are the characteristics of the filters, but the basic underlying construct is retained. The thing I want you to also notice is through this deep architecture, we're able to go from fundamental atomic building blocks to rather complex structure. We're going from single cell to multi-cell organisms in this way, of course, notionally, right? So And then finally, it should be pretty clear why this is deep, at least why the architecture is deep. This is what we mean by deep. So what we mean by deep is a multi-layer manifestation of a fundamental construct, which here is convolving filters across an image or feature maps. And then finally, we take the highest layer features, and then we would send those into a classifier to make a classification decision. So typically, not always, but often, the classification decision is made by the top layer features. And so therefore, the top layer features are characteristic of those complex high-level motifs. But the way that we do this is through this hierarchy. And so these features are then sent into a classifier. If we're doing a binary problem, so for example, we're trying to do a diagnosis of malignant versus benign tissue, that classifier could be logistic regression. So we're all very comfortable with that. So that pick your favorite classifier, stick it at the top. Now, the question that was asked was, do we know the filters? And in my toy, up to this point, I assumed I knew the filters, but of course we don't know the filters. And in fact, different problems will have different filters. So it depends upon what problem you're solving, and it depends upon the data. So how do we learn these filters? Well, one of the great things about the current state of the world is we got a lot of digital images. Everybody's taking pictures on their cell phones. And increasingly within hospitals and other places, images are being digitized. And so we have a tremendous quantity of images. What we're going to do is we're going to use that massive quantity of images to learn the filters. So let's see how we're going to do that. Before I do that, before I go forward, any other questions?
We have two questions. One is, are permutations of atoms in the motifs distinguishable?
I'm not exactly sure what is meant by the word permutation.
I'm guessing they mean the arrangement of the building blocks in the motifs.
Yeah, so the order of them is totally arbitrary. So there's no meaning to the ordering here. And so, okay, so yeah, you could permute the order of these guys any way you want. And then these filters will just permute similarly. So so we don't worry, there's no meaning to the order at all. You could flip the order and nothing changes. Okay, so all right, so how are we going to learn these filters? Well, what we're going to do is we're just going to play the same exact game, except that instead now of saying that I know what these shapes are, I'm going to call those functions. Phi1, Phi2, Phi k, those are filters. They're K filters. Those filters are composed of pixels. This is an image. They're composed of pixels. The values of those pixels are unknown. I want to learn them. Okay, so I don't know what they are now. I'm going to call them Phi1 through Phi k. They're K filters. Now, a question you might ask is, what's K? How many filters should I have? Well, there's no theorem here, actually. And the reality is, the perhaps unfortunate reality is, you experiment, you try different things. Now, the state of the field is such that people have a very good sense of what K should be. But the point is, there's no theory about that. It depends upon the complexity of the data. But in any case, so Phi1, Phi k, those are our filters. Those are now functions. We want to learn them. Let's just assume we knew what they were. In other words, at a given, when we do learning, we're going to do learning through an iterative process, iterative learning. So within our iterative process, let's say at one iteration, let's say that we have these filters. we play exactly the same game. Take the filters, convolve against the image. We get, and we have K filters, we got K feature maps. Let's call that M sub n. So I sub n is the nth. We got a lot of images here. Sorry. IN is the nth image. MN is the feature map at layer 1 for image n. It's a function f of the input image and then those filters. This is the 2D convolution, so it's a simple function. And now the layer 2 filters, I didn't stack it here just for simplicity. So I didn't show the stacks, but these are stacks in the same sense that we talked about before. Let's call those psi 1 through psi k. Next question, does k have to be the same on each layer? No, doesn't. I'm just letting it be k for simplicity. Those filters psi 1 through psi k are unknown, but those are functions. Those are just values of pixels. Let's assume we know what they are at a particular iteration. Then this layer 2 feature stack or feature map, stack of feature maps, we'll call that L sub n for image n. It is a function. It's the same function. It's a convolution, 2D convolution of the layer 2 feature map. And these filters, this is the layer 2 feature map. And then we'll call layer 3 omega 1 through omega k. Does k have to be the same? No. But omega 1 and through omega k are unknown, but they're just filters composed of pixel values. So let's assume we know what they are at a particular iteration of the learning. And so we'll call the layer 3 feature map G sub n. So this is exactly the same thing that we talked about before, but now instead of making cartoon pictures, I just call them functions. Those functions are unknown. How do we learn them? Well, we have a lot of data. We got pictures of dogs and cats and birds, and people have labeled those images for us. And so what we're going to do is we're going to predict the label. So I'm calling here script L is the label of the image. So, this could be dog, cat, whatever. Could be benign, malignant, could be whatever the problem is. This is a function of Gn, which are the features at the top, and W, which are the parameters of your favorite classifier or labeler. Doesn't matter, whichever one you like, use it, okay? And so then what we do is we constitute a loss function. So let's assume for simplicity that we have n images. In is the image, the nth image. Yn is the nth label. And for simplicity, we're going to just assume that Yn is binary, +1 or -1. But we could do it, it doesn't have to be binary. Yn is our label, In is the images, we got n images. N could be like 1 million, could be tens of millions. We got a lot of data. And what we do is we constitute a loss function, which quantifies the error or the loss between the true label, Yn, and the label of our model. We just sum up the total loss, call that the error. The error is a function of P1 through Pk, psi 1 through psi k, omega 1 through omega k, and W. Those are the parameters of our model. Those are unknown. However, now I have a loss function. So now the game is try to minimize that error and then choose the parameters phi, psi, omega, and W that minimize that error the most. The way we typically do that is with gradient descent. But pick your favorite optimizer, you can use it, whatever you like, okay? Now, that is a very high dimensional parameter space that you're trying to optimize. The number of filters here could be substantial, could be large. And so therefore the total parameter space is quite large. And, you know, I can't draw a picture in any higher than 2 or 3 dimensions, you know, but you're talking about, this is, you know, here, this is, let's say the error as a function of 2-dimension of parameters. So obviously trivial, very simple, but of course we could be talking about 1 million parameters to learn. It could be 10 million parameters to learn. So very, very complicated space with many, many local minima. So there's no way in the world you're going to get the global optimal solution here. But kind of the miracle is that this model is so well constituted from an intuition perspective, the intuition I tried to give you at the beginning, that it turns out that when you do this optimization, you can get many, many local optimal. And it turns out that many of them work about the same. There's a lot of redundancy. So the kind of the bad news is, there's no way in the world you're going to get the global optimal solution to this problem. And depending upon where you start your gradient descent, you'll get very different answers for your model parameters. That's the bad news. The good news is it doesn't matter, because today we actually don't really care about the model parameters, although we need the model parameters. We care about our capacity to predict what this thing is. And it turns out that there's a lot of different ways to constitute these filters and to get good results. And this actually ties to the question that was asked earlier. Can you permute the filters? And the answer is yes. But permuting the filters doesn't do anything to the final result. And so consequently, whenever you do learning of these filters, despite the fact that we do not have an identifiable unique solution, it doesn't really matter, because it's kind of like doing a permutation, for example, and they all basically are the same, okay? Now, what do these filters look like? So these are the layer 1 filters. So each one of these is a filter. Black means strong, white means, black means positive, white means negative. So if you look at this, this is negative, positive, negative. So it's like a sine wave. It's like 1.5 cycles of a sine wave. It's called a Gabor function. So the thing I want you to notice is that the filters that you learn at the bottom layer, the most primitive filters, those atomic building blocks at the bottom, they are rotated versions of a Gabor function. And you find this invariably. This is characteristic of images. And the remarkable thing is that people have studied the most primitive atomic image that mammalian eye will respond to by studying the brain. In other words, so people have done studies with animals where they show images to the eye, and they look at the neuron firing in the visual cortex, and they ask the question: what image could you project on to the retina of an animal for which you would trigger the most elemental, in other words, like a single neuron? And it turns out that they look very much like these Gabor functions. So that gives us a lot of it gives us some reassurance, if not confidence, that maybe we're on to something. This is the layer 2 filters. This analysis was done on images of faces, for example. So I want you to notice like this filter right here. It looks a lot like an eye. This looks like an eye. Maybe this is a nose, another eye. These are the layer 2 filters. I think kind of cool. And then these are the layer 3 filters, or layer 3 motifs. Notice that you're starting to see sketches of a face, a sketch of a motorcycle, a sketch of a car. These results are based upon numerical analysis on a large quantity of images. Okay. Okay. Let me pause and see if there are any questions.
So we have a question about generalizability outside of the training sets.
Okay, this is a very good question. It's a very good question. So the question is, if I train an algorithm to learn these filters based upon, let's say, natural images that might exist of dogs and cats and things like that, does it generalize to other problems? For example, analysis of the retina of the human eye, which doesn't look anything like a dog or cat or anything. And what people have discovered is that if you take a database composed of natural images, let's say of dog, cats, and whatnot, and those images are labeled, in the sense that I talked about earlier, and you learn these filters. You learn phi 1 through phi k. You learn psi 1 through psi k. You learn omega 1 through omega k. Can we take those filters and transform and utilize them for a different imaging task? And the specific task that people have done this for is something called diabetic retinopathy, which is a comorbidity associated with diabetes. If it's diagnosed early, it is curable. If it's not diagnosed early, it leads to blindness. So a very stark outcome depending upon early diagnosis. People generally do not get checked as much as they should for this. And so the question was, could we use AI, deep learning, to do this automatically? And the answer is yes, and you can do it as accurately as a human ophthalmologist, actually more accurate. So the question that these guys asked in that work was, could we just take phi 1, take the phi, the psi, and omega? Because in ophthalmology, you do not have millions of ophthalmology images. We don't have millions of images of diabetic retinopathy. I got millions of images of cats, but I don't have millions of images of diabetic retinopathy. So if we could transfer those filters, it would be enormously powerful. And the answer is you can. And so the only thing you have to change, you got to change the classifier in the top, because clearly you're doing a different problem. So what these guys did, which is actually remarkable, they took an algorithm which was learned based upon natural images, dog, cats, and the like. They took the filters, phi, psi, and omega, took them directly, no change. And the only thing they did was change the top, the classifier. And they made a new classifier, which was trained on images of diabetic retinopathy. Now, the number of images we have is substantially smaller. It might be like thousands of images. But the number of parameters we have to learn is also substantially less, because we only have to learn the weights of our classifier. So the answer to your question is absolutely transferable, which is extraordinary. Now, but if you think about this a little bit, maybe there's some logic to it. So let's think about this. So imagine that you're a young medical student, and you are now going to be trained to look at images of the eye, and you're going to be trained to do diagnosis of diabetic retinopathy. You're a 25-year-old person. You've done a lot of looking at the world for the last 25 years. You've seen a lot of images. And so the question is the mammalian visual cortex system transferable? Whenever you look at images of diabetic retinopathy, are you able to transfer the knowledge you have of colors, shapes, textures, all of the motifs in my example at the beginning? The question is, are the motifs of the eye for diabetic retinopathy, are those motifs, at least some of them, are they transferable from motifs associated with dogs, cats, and whatever? The answer is yes. And this is what human, if I had to learn how to see every time I saw a new type of image, learning would be quite difficult. And so what appears to have happened is the visual cortex is generalizable. And basically, whenever a medical student learns how to do diagnosis of diabetic retinopathy, effectively what they're doing is they're changing their classifier at the top. But the features that they're looking for, colors, shapes, texture, are the same. So intuitively, it should be transferable. And it turns out it is transferable, which is a remarkable thing. It's hugely important. Okay, so all right, so now this we have a lot of statisticians on this call, I think. And if you think about what we've done here, we haven't actually modeled, we have not modeled the image. What we've done is we've extracted features from the image. So this is actually kind of the difference between, say, machine learning and classical statistics, because in classical statistics, oftentimes we like to build a generative model of the data. And we're going to talk about that this afternoon. So deep learning can do that too. But nevertheless, let's just keep going. So the question is, can we take these features at the top and go backwards? And this is called deconvolution. So this process, what we were talking about before, going from bottom up, it's a 2D convolutional process. If we take the features at the top and go down, our objective is to reconstruct the image. So image in, image out, I hat is our approximation to the image, I is the image. We would like I hat to be real close to I n. Okay, so now we have, so now why would this be useful? Why is this useful? The process that I talked about before assumed that we had a label for every image. Remember, we had a y sub n for every image. It's actually quite expensive for human beings to label these images, and moreover, they can make errors. And so when we introduce this, what we call generative process, and this is a process that statisticians often feel comfortable with, is to build a model of the data, then we can analyze unlabeled images, because I don't necessarily need this classifier. And so now what we have is a feature extractor, and then a generator from the image. We have a generator from the features, and then we have a classifier. So when we have labels, we use them here. But when we don't have labels, we can still use those data, and we just don't use the classifier. And so the left-hand side is called an encoder. The right-hand side is called a decoder. And this thing is called an autoencoder. So it's an encoder, and it's a decoder, It's called an autoencoder. This is a term that's used in the machine learning community. The nice thing about this is that you don't need any labels to do this. But anyway, stepping back, so this is a feature extractor, and this is a generative model. Now, what do we learn on? So now there's a data set called ImageNet, which is composed of 1.2 million images. So what you're looking at are thumbnails of a lot of images. Those images look like what you see on the bottom here. So, you know, this is a blow up of 3 of those images. And every one of those images is labeled. There are 1,000 different labels, so 1,000 different classes, and roughly 1,000 examples for every label. So roughly 1 million labeled images. What we're looking at here, I'll try to explain this. So all of these data are labeled. But what if we only had 1% of the data labeled? So what we're going to do here is we have 1.2 million labeled images. We're going to only utilize labels on, say, 1%, 5%, 10% of the images, and the remaining 99%, 95%, 90% will be unlabeled. This is we're trying to synthesize, because we actually have the labels here, but in practice we don't have the labels. And the question is, how well does learning based upon unlabeled data help us to do this labeling task? So let's think about this a little bit. You think about a little child, and a little child, young kid, 1 year old, whatever, when they first learn to speak, they'll drive the parents crazy, right? What's this? What's that? Now, if you think about it, what's happening is the child is acquiring labels. But at some point, the mother or father get totally disgusted at all these questions they just don't want to answer. But yet the kid's still looking around, still getting a lot of data. It's just not labeled. And so, what the human brain is doing is it's learning on labeled data and unlabeled data. Well, what's the value of the unlabeled data? Because we don't have labels. Well, the unlabeled data teaches us a lot. It tells us a lot about structure. It tells us about shapes, texture, color. I don't need any labels for that. And so what we're doing here is looking at performance of deep learning. This is my group's work. As a function of the fraction of data that are labeled. So here, 99% of the data is not labeled. And we can still get roughly 60% accuracy in classification. Now you ask, how good is 60%? Well, actually 60% is very, very good, because we have 1,000 classes. This is not flipping a coin. We have 1,000-sided coin. If you want to flip a coin, there are 1,000 different classes. How well does conventional deep learning do whenever you have only 1% of the data? Well, it falls apart. So this is the Google model. And so this is one of our early contributions. So this shows that if you use the unlabeled data, you can get a significant gain in performance. But of course, as the amount of labeled data increases, the performance of our algorithm increases. How well does this do? Well, we're getting on the order of around 90% accuracy in classification, where there are 1,000 different things that it could be. That's actually incredibly accurate. And where the field is today is it's more accurate than humans. So let me pause, see if there are any questions.
One question is, what about overtraining on the training data set?
So what is typically done is we have what we call a holdout data set. So we have a training set, and then we have a holdout, what we call validation set. And so what we do is when we do gradient descent, the danger is if you do gradient descent too long, you have the potential to overtrain, and you will basically memorize the training data and not generalize well. And so what we do is we use a validation data set, which is a holdout data set that we do not train on. And we evaluate on that evaluation set periodically during the gradient descent process. What you find is on the evaluation data set, as the number of iterations of training increases, the error, decreases. In other words, it gets good. And then as the number of iterations increase, then you start to see the error on the holdout or validation set start to increase. And then you stop. And this is called early stopping. So we do not run gradient descent to convergence. We look at the validation set, and when the so early in the gradient descent, you see the performance on the validation set, the performance improves. And then as the number of iterations of gradient descent increases, eventually you start to see the error on the held out data set start to increase. The error increases. You stop. This is called early stopping. Okay. Okay. So let me. We're kind of coming to the end. So let me just kind of talk about why does this work. So first of all, hopefully you now have a sense of how this works. You have a sense why we call this deep learning. The deep part should be clear. Now the learning part should also be clear. We're going to learn these filters. But okay, and then the performance is great. Like on tasks like diabetic retinopathy, the performance exceeds the performance of a board certified ophthalmologist, which is stunning. And we've seen similar performance in ophthalmology, radiology, and many fields, dermatology. So why does this work? We go back to our analogy. So if we look at these high-level motifs again, so let's think about this if we did not use deep learning. So imagine we did not use deep learning, because remember that the classifier is only based upon the high-level motifs. The classifier is only based upon the high-level motifs. So why do we have to do this deep hierarchy? Why don't we just learn the high-level motifs? What's the advantage of this deep architecture? Because at the end of the day, the classifier is based upon these features. We don't even use these features down here. So why is this a good thing? Okay. Okay. So the thing is, we have these high-level motifs. Some of these high-level motifs may be relatively rare. They don't happen that often. So like this motif right here, maybe that only occurs in a relatively small subset of images. And if we were to learn the high-level motifs only at the top, in other words, don't even do this hierarchy, then we're only going to be able to learn this high-level motif on a relatively small amount of data. However, if we do this deep architecture, we're able to share what we call statistical strength. That even if this motif only occurs a relatively small time, I am going to be able to learn about this substructure from all of these other motifs. So there's the capacity to share statistical strength, the capacity to share data. Likewise, if we were to learn these motifs independently, then there's no capacity to share in the understanding of what that atomic element is. And having an understanding of the atomic elements helps our ability to learn. So like, for example, if we have an alphabet of letters, 26 letters of the English alphabet, and if we know what that alphabet is and we see a word, but maybe one or two of the letters are missing, well, we know the alphabet and we know the structure of language. We can do a pretty good job of imputing what those letters would be. The same thing happens here. We know what a triangle is. So even if an image were to have kind of a noisy triangle here, but this was clear and this was clear, then you would probably be pretty able to identify that that's probably a triangle. However, if you learn these filters independently without the sharing through this hierarchy, then you lose that capacity entirely. So this deep architecture has a lot of advantages. Now, let me just conclude because I don't want to go over. In the previous results, I showed a classifier where the only objective was to label the image. But we could go beyond that. We could put a language model on the top there, and we take the features, and then using those features, we run it through a language model, a neural network language model, which I won't talk about here, and then we can spit out text. Well, how well does this work? And so what you're seeing here are results from a machine where the machine was given an image and then was asked to automatically produce a description of this image. Now, if you think about this task, it's actually pretty remarkable because first the algorithm has to analyze the image and figure out what is in the image, and then it has to write or describe it in idiomatically correct English. And so now, if you look at this, it's a big black dog standing on the grass. Okay, so this also shows the pros and cons, or the good and the bad. All right, that's a dog, and the dog is standing in the grass, but it's probably not a very big dog. It may be, actually, I don't know, but it kind of looks like a small dog to me. But the problem is that the machine doesn't really understand that. It just knows that the dog takes up the whole image, so probably a big dog. So it shows the good and the bad. Here's another example, a box full of apples and oranges. Well, I think those are lemons, but you can see it's not too bad. Okay, so let me now finish. This is the big picture. Deep learning is a deep convolutional structure where we're trying to learn these filters. We take training data and we set up a loss function and we do gradient descent. Okay, so we set up a model, we take training data, we set up a cost function, which we try to minimize. Now there's a lot of technical details I don't have time to go through, but this hopefully should give you a sense of the big picture of deep learning. This afternoon, I'm going to give another talk. It will be more technical, meaning at least more equations, and it will also cut at the state of the art of deep learning. So thank you so much for your attention. If there's one more question, I'm happy to take it.
So one last question is, if we are not as interested in the particular filters and model parameters, is it hopeless to interpret this model? So
I think we're increasingly gaining insight into interpreting it. So, and I tried to give some intuition as to what's going on in this model. So what I would say is 5 years ago, people would call this a black box model, which means opaque from the standpoint of understanding. Today, I think that's not true. While it's still rather complicated, I think we have a fairly clear understanding of what's going on. You could ask the question, do we understand the visual cortex of the human brain? The answer is no. But it seems to work pretty well. We don't understand the human visual system. We probably understand this better than we understand the human visual system. Okay, so again, thanks everybody. I will be doing a different one this afternoon. Hope to see a good number of you guys.
Thank you, Larry. Yep.
Okay, excellent.
Yeah, thanks, Dr. Carin, for a very insightful and intuitive talk. I hope we all learned something from this. For all the viewers, we would appreciate you sharing any feedback you have on how you thought this seminar went. There's a link on the seminar page on the department website that you can submit your feedback. And yes, please join us later this afternoon at 3:30 for Dr. Carin's second talk titled on demystifying adversarial learning. And we look forward to seeing you all then.
All right. Thank you.
Thanks, Jerry. See you afternoon. Bye.
Okay.